functions have this form, p of x over q of x, where p and q are each polynomial functions. And in looking at an example of one of these things, say 2 over x plus 1, you see that the graph has this strange behavior near x equal negative 1. Can anyone tell me anything special about x equal negative 1? What do you maybe notice about the form of this equation that says x equals negative 1 is going to be worthy of interest? Brandon?
It'll make the denominator 0.
Yeah, it's going to make the denominator 0. So that's a problem. So we've got this little slider here, and we can kind of keep an eye on things, points on our graph, as we get closer and closer to, say, a denominator of 0. Now, a denominator of 0 is going to happen when x is getting closer to negative 1. So let me kind of get closer to negative 1 and watch what happens to this total a plus 1. So as x is negative 0.93, 1 plus negative 0.193 is 0.07, and then 0.065, etc. And so what's happening? Well, the closer I get to negative 1, what's happening to my y coordinate? It's increasing. It's getting bigger and bigger and bigger. It's moving up that y-axis towards where? What do you think is at the top of this graph? Yeah, positive infinity. Now, something unusual happens when I cross over the line x equal negative 1. If I start approaching negative 1 from the right, now this quantity is negative, but it still has kind of a similar behavior. It's just that now when you divide 2 by this small negative number, now we're getting closer and closer towards negative infinity. So depending on the sign of this, you're either going to approach positive infinity or negative infinity. Either way, x equal negative 1 is kind of special. And I'll put it on the graph like this. That's a vertical asymptote. There's also one other thing that's worth noting, and that is this graph kind of eventually flattens out. When I get bigger and bigger numbers, the ratio of 2 over some really big number is going to go out towards, well, what happens to this graph? It flattens out towards what value? Yeah, towards 0. So when you put in a number like 999, then you got 2 over 1,000. Or you can end up with 2 over 1,000,000 or 2 over 1 billion. Eventually that's going to get exceptionally close to 0. So there's 2 what are called asymptotes for this graph. So one of them is a horizontal asymptote, and one of them is a vertical asymptote. Looking at this example on your handout, if I asked you what's the asymptote, well, for this one I would expect you to answer y equals 2. Please don't give me just 2, because 2 could mean x equal 2 or y equal 2. It's not quite clear enough. Then on the flip side of things, you've got this line here, and that looks like a vertical asymptote. What's its equation?
X equal 2.
X equal 2. Thank you. And you could also be asked for the end behavior. Now, we'll see a better example towards the end of this, but the end behavior really should come with another little thing here. As x approaches positive infinity. So as you're going out the x-axis towards positive infinity, that's going to mean we're heading out this way. We want to know what's the y-coordinate getting close to. So if I go out this x-axis towards positive infinity, what y value am I getting close to? Positive 2. Yay. So as x approaches infinity, y approaches 2. What if we go in the opposite direction? What if we go x approaches negative infinity? So we're going out this way. Where does the y coordinate approach?
Towards 2.
Still 2 again. Now, these don't always have to be the same value, and maybe later during one of our review problems, we'll see a place where they're not. So this is just trying to establish some vocabulary here. What we're going to have to do is get used to trying to find some of these things, understand where they occur, etc. And I'm going to kind of skip down to example C first, and then we'll do a few more, and then maybe skip back to example B, because there's something special about example B that's a little atypical. Does example B have any vertical asymptotes? Is there a place that kind of looks like this line here, x equal 2? No. It has kind of a dip, but there's no vertical asymptotes. So a quick no on that one. X-intercepts. Where are this graph's x-intercepts?
4 and negative 4.
Yep. 4 and negative 4. So 4 and negative 4. And does it have a horizontal asymptote?
Yes. Yes.
Yep. Y equal 2. So let's throw that one in there as well. Y equals 2. Does it have a y-intercept?
Yes. Negative 6.
Negative 6. Now, WebAssign might want 0, comma, negative 6. I'll be just happy with negative 6 on an exam. So that would be this point down here at negative 6. Beautiful. Let's try and understand how we can predict where some of these places are, find some of these values, and we'll do that with our next one, example D. And I asked you to find several things here, vertical asymptotes and horizontal asymptotes. We'll do a little bit more as well. Now, let me pass this around. This is going to be a way to find our horizontal asymptotes. So there's going to be 3 cases of finding your horizontal asymptotes, but let's start with finding your vertical asymptotes. So example D, I'll make this page 2. Example D gives us this function, f of x equals 16x squared plus 1 over 4x squared plus 10x minus 14. I'm going to start by helping you find the vertical asymptotes. So it's nice that we can predict a lot of things about the graph just based on the form of the equation. Just how does this equation look? All right, well, it looks like this. So, oh, I have vertical asymptotes here and here. So vertical asymptotes. Oh, it's not writing too well. Asymptotes. To find these, you're going to set the denominator equal to 0. And in case you didn't pick it up on the first example that we kind of looked at in depth here, this one over here, where the denominator is 0, that's going to tell you where this vertical asymptote is. By the way, it tells us something else. It tells us something about our domain. I can't let x equal negative 1. You see the result of trying to deal with x equal negative 1. You've got this crazy little vertical asymptote here to contend with. So vertical asymptotes, to find those, you're going to set the denominator equal to 0. Equal to 0. So that's going to mean 4x squared plus 10x minus 14 equals 0. Personally, if you ask me to solve this one, there's something that I would do before I really got down to the business of solving. Can anyone suggest what that might be? Yeah, I'd get rid of the extra factor of a 2. If you notice that 2 goes into each of these, let's just divide both sides by 2. Now I'll be very helpful. I'll do the right-hand side for you. 0. What do you got on the left? Well, 2 into 4 goes twice. So 2x squared plus 5x minus 7 equals 0. That's not a whole lot easier than what it was, but it might make it a little bit easier if you're going to try and factor to solve this. If you're not factoring to solve this, what's your alternative?
Quadratic.
Yeah, the quadratic formula. Yay. So the viewing audience cannot hear the enthusiasm with my students said quadratic formula, but it was there. In any case, if I'm going to factor, I know I need a 2x and an x. The last two numbers have to multiply to -7. So there's only a few choices I can put in. I can put in a 1 and a 7, or a 7 and a 1. I can put in a positive and a negative, or a negative and a positive. That's a total of 4 choices. So this one's not too bad to try and mess around with. If I put the 7 here, I have 2 times 7 would be 14. And it doesn't feel very likely to me that I'd be able to get a 5 here in the middle. So I'll put the 7 here and the 1 here and let you play around with the signs. Which one's positive, which one's negative. Has to be one of each. Any winners?
Plus
Plus
1.
Good. +7 minus 1. Now, like I said, your backup in this one is the quadratic formula. There's nothing wrong with the quadratic formula. Just unfortunately, it takes a little longer. No big deal. So, we got 2 possible solutions. Oz, what are those solutions?
I thought I had, huh? Wait,
Where could this equal 0?
oh, with a 1. I mean, yeah, 1.
And where else? So -7/2 and 1, those are our 2 places where the denominator could be 0. And that tells us a couple things. So first of all, our vertical asymptotes that would be x equals -7/2 and x equal 1. Seems like you still have a question. Go ahead.
No,
Please. This also tells us something else. If I put in a 1 here, what would that make the denominator equal to? 0. Can we have 0 in the denominator? No, we can't. So our domain can't include those points. So let's draw ourselves a little number line here. And we've got points at -7/2 and 1 that we have to exclude. What would that look like in interval notation?
Parentheses, negative infinity to -7/2.
Good?
Union, -7/2 to 1. Union, 1 to infinity.
Awesome. Thanks, Sabira.
No problem.
So there's your domain. It's everything but those points. All right. Nice. Nice. So we got the vertical asymptotes, we've got the domain. There's another feature of this graph that's worth noting, and that is the horizontal asymptotes. Now, our horizontal asymptote has one of several possibilities. So let's take a look at that little handout that I passed around and look through those. For horizontal asymptotes, we have to play a little bit of a game. We have to decide what case we're dealing with. is it case 1, case A? So case A, if the degree of the numerator is less than the degree of the denominator, then y equals 0 is your horizontal asymptote. Now I'm assuming that we have some kind of a rational function. Our r of x is p of x divided by q of x. That's the form that I'm assuming. And then we can look at the degree of the numerator divided by the degree of the denominator, or just compare the degrees here. By the way, how do I determine the degree of a polynomial? What's the degree of the numerator here, for instance?
The biggest power, so
Yeah.
it'd be 2.
So the degree here would be 2, the degree here would be 4. Perfect. Let's see.
Why is it 4?
Oh, excuse me, sorry, the leading coefficient is 4. The degree here is 2, and the degree here is 2. My bad. I was thinking ahead to a little something I gotta do next.
Add on to my coefficient.
I know. Now, if the degrees are equal, then it's going to be the ratio of your leading coefficients as to your horizontal asymptote. And the very last thing we're going to consider is what's called an oblique asymptote or slant asymptote. If the degree of the numerator is 1 bigger than the degree of the denominator, then if you divide this and get a quotient and remainder, y equals the quotient, that's going to be your horizontal or your oblique asymptote or slant asymptote, as I think the book might call it sometimes. Okay, well, let's see what we got in store for us here. Try and look through this and decide which case you think we have. You have case A, case B, or case C. Try and figure out which one we have.
Case
I thought B was one part of the other.
no, that's
The leading coefficient.
So what you want to do to decide which case you're dealing with is
It is.
look at the coefficient, or look at the degrees and see, do they match? Is one less than the other? If so, is the numerator less or is the denominator less? Let's vote all together with our voice. Which case is it? A, B, or C? B, good. So we have degree 2 and degree 2. That means our horizontal asymptote is just going to be the ratio of those leading coefficients. So it's going to be y equals 16 over 4. And I'm purposely putting these in color so that you can kind of look back at what I wrote up above and match things up. 16 over 4, that reduces to y equals 4 as your horizontal asymptote. Great. Let's find a couple more things while we're here, or at least look for a couple more things. I think we're only going to find one of them. How about the y-intercept? How do you find the y-intercept of a graph? Yeah, set x equal to 0. So if I do that, I get f of 0 is 16 times 0 squared, etc. Let's put that in. Plus 1 over 4 times 0 squared, plus 10 times 0 minus 14. 0, 0, 0. What am I going to end up with for my y-intercept? 1 over 14. There's a negative here, so I'll just kind of tuck that out front. So negative 1/14, that's my y-intercept. And finally, let's do the x-intercept. How am I going to find my x-intercept?
Set everything equal to 0.
Yeah, set y equal to 0. So my y in this case is going to be this term right here, the f of x. So that's going to be 0 equals 16x squared plus 1 over 4x squared plus 10x minus 14. Solving this is going to be a lot of fun. All right. So I'm joking a little bit, but we can make our life a lot easier by getting rid of the denominator. Now, in any equation, when you're solving, assuming you're working with an equation and not just an expression, something that has an equal sign, I can multiply both sides of the equation by something. In this case, if I multiply both sides of the equation by, I don't know, the denominator, what's going to happen when I multiply both sides of the equation by the denominator?
Turn into
Yeah, so on the left-hand side, I get 0, right? It was 0 before, times something is still 0. On the right-hand side, I get 16x squared plus 1. So let's solve for x. I'll move everything over and divide by 16. I get x squared equals negative 1/16. What do I have to do to solve here? Take the square root on both sides. So let me just switch those. Thank you. And I need that plus or minus. Now, hopefully you don't get too excited here and overlook something. You've got the square root of a negative number. What happens when you take the square root of a negative number?
You get an I.
You're going to get an I. So in this case, we get plus or minus 1/4 I. So if you're looking for where this crosses the x-axis, it only does that in your imagination. You're not going to see a place on the graph where it actually touches the x-axis. Let's put all this together with the graph. All right, we've got a lot of features of the graph, so no real intercepts. We've got a horizontal asymptote at y equal 4. That's cool. We've got two vertical asymptotes at x equal negative 7/2 and x equal 1. And we've got a y-intercept at negative 1/14. So we can look for all these things. Someone give me a calculator value, please, for negative 1/14. While I pull up the graph. Let's see, let's shut this one off. And shut those off. What else do I have turned on here? There we go. So I'll look at example D here, which is this graph. I'll start by plugging in or turning on the asymptotes. So here's our asymptotes. This frames a lot of the graph that we're dealing with. Now, I kind of regret there's a little feature in Desmos that I could change things up a little bit. Probably would prefer to make these dashed lines. And the reason for that is because they're not really things that are part of the graph, but they do kind of help frame our graph. And it's nice to have them drawn so you can kind of see where they're going, but they're not actually part of our graph. Now, as far as the rest of the function is concerned, let's take a look at that. There's your graph. So it's really the stuff that's in G. Now, it looks like this touches the x-axis, doesn't it? I said it didn't. If you zoom in enough, you'll see that this point touches at negative 0.017, which is about negative 1/14. So it doesn't quite touch the x-axis. It has the vertical and horizontal asymptotes that we expected. But on your test, you're not going to be using Desmos. You're going to be using your graphing calculator. So let's take out your graphing calculator and learn a little bit on how to put this in. All right, so calculator workshop loan program is open for business. First customer of the day, you get 10% discount.
Turn into extra credit.
There you go. You. You. There's a couple different ways you can put this into your calculator. Let me go through both of those. I've got some stuff here from a different problem.
What are we looking for again?
We're just trying to graph it right now on our graphing calculators. I want to give you a little experience in doing that. So let me clear out some old stuff here. And I'll clear this out as well. So if you press the Y equals key, one way to plug this in is with parentheses around the numerator. So parentheses 16x squared plus 1, right parenthesis, divided by, and then left parenthesis. Now if you kind of fall behind my calculations here or my work here, you can use the keys on the bottom of our calculator to kind of see where things are at. Divided by 4x squared plus 10x minus 14. So that's one way you can input things. Now, a perhaps better way that you can't do with all your calculators, for instance, the TI-83 won't do this, which is kind of annoying, but it's a little bit safer for certain problems. If you hit the alpha key, then the Y equals key, that'll give you the option to do a straight up and down fraction. And now I don't need to worry about the parentheses anymore. 16x squared plus 1 divided by 4x squared plus 10x minus 14. So again, to get that option, you're going to hit the alpha key, the Y equals key, and then enter, or type the number 1. Those three keys right in a row here, and that'll give you that straight up and down fraction. As far as where you graph this is concerned, if you're looking at this and go, I don't know where to graph it, then a good place to start, and you can always adjust things as needed, is zoom standard. So that's zoom and then the 6 key. That gives you a window from -10 to 10 on the x-axis and -10 to 10 on the y-axis. And looks like I might have made a mistake here someplace putting in my function. Oh, I forgot the x in the denominator. I was going to say both of those graphs should have been one on top of the other. If you need to make a correction, like for instance, I need to put in an x here, and you're like, oh, I don't feel like typing that all over again. You don't have to. Take a look above the delete key. What do you see in blue above the delete key?
Insert.
Insert. Second, insert. Now I could type my x and it just moves things over. So kind of cool. Now if I hit graph, you'll see it draw the blue graph first, and then right on top of it, it'll draw the red graph over it. So you gotta watch kind of quickly. Bam, bam. There it is. Both graphs are the same.
Bada bing, bada boom.
It's not gonna graph for you these vertical and horizontal asymptotes. I mean, you could make it graph the horizontal asymptote. If I ask it to graph y equals 4, for instance, well, then it puts it in there for me. I can see that, yeah, the graph is getting close to 4, but it doesn't quite touch 4 once you get out way far away from the y-axis in the x direction. Okay, are we okay with all that? There was a lot in this example, but all good stuff that I would expect you to know and do.
Can you show like the bottom right of that page? No, that
Oh.
one you're just on.
Here? That one, yeah. So this shows you that there's no x-intercepts. The graph does not cross the x-axis. And we saw that in particular when we zoomed in here, because boy, it looks like it touches at x equals 0, but if you zoom in enough, you can see there's a little gap there.
How do you
It doesn't
know-
quite touch.
How do you know from looking at that, from looking at the equation that that's not touching 0?
Because if it did touch 0, I would get a real number.
Oh,
This only crosses the x-axis in your imagination, is kind of the cute way I like to say it, but because you get imaginary numbers, that's why you know that it doesn't really touch the x-axis.
but that means there could still be a y-intercept.
Yeah, there is a y-intercept. You get the y-intercept by setting x equal to 0.
Okay.
It's weird, like graph.
All right, so let me show you a little thing about the graph of the TI-83. The way your graphing calculator works is it divides your screen into 94 points. And then for each x coordinate that it finds, it says, all right, I'll need to find the y coordinate. And what's happening with the 83 is that it finds a y coordinate down here, and then the next point it finds a y coordinate up here, and it's trying to play connect the dots. So that's why you're getting this strange stuff in here, is that it doesn't really know that there's a vertical asymptote, and it's just trying to play connect the dots. So that's kind of an annoying thing about this. I think there's probably a way around it if you set your window quite nicely, like maybe negative 9.4 to 9.4. That would probably put one of your asymptotes. No, it's still doing that. It's a little bit better, but it's still doing that. Yeah, it's just tough to get around for some of your older graphing calculators. I'm not sure what the newer ones are doing that so that they don't show that, but they don't seem to. All right, thanks, Ace. Let's take a look at example E, unless there's some more questions about example D.
I have a question.
Yeah, please, Mina.
How is y equals 4 horizontal asymptote?
All right, so good. Why does y equal 4 a horizontal asymptote?
It touches that 4 if you look at the graph.
Well, but what makes it a horizontal asymptote is not what happens near the x-axis. It's what's called the end behavior. It's what happens when you're way out towards infinity or negative infinity. Now, it's of course tough for us to get there, that is negative infinity and infinity.
But there,
But
it's right there.
if you, let me, let's see. Let's see where. If I zoom out in the x direction, can you see that this graph kind of settles down near 4
Yeah, but
or
Right.
positive 4?
it intersects 4 right there.
That's okay. I mean, it could do whatever it wants when it's close to x equals 0, which is your y-axis. But the end behavior is what happens when you get very, very far away from the y-axis out towards x equals, say, infinity. And as you get out towards infinity, I mean, look, even Desmos says, yeah, I'm just going to round this to a 4. Although if you come in close enough, let's see, no. All right, I'm on the wrong one. Let me, here we go. If you take a look at the y coordinates, they're getting steadily closer and closer to y equals 4 as they move out the x-axis. And as you approach, let's see, I keep on, let me just shut off that. As I approach, positive infinity, that number for the y coordinate is getting closer and closer to 4. So that's how it's a horizontal asymptote. It doesn't really matter what happens when you're in close here. The horizontal asymptote part of it is what's happening when you get out far away from the x-axis. Here we're a little bit above 4. Here we're a little bit below 4, but eventually it closes down on 4. And that reflects the fact that when we looked at the ratio of the leading coefficients, you had a 16 and a 4. And 16 over 4 reduces to y equals 4 for your horizontal asymptote. Good?
Yeah.
All right, appreciate the question, thank you. Let's move on to example E. And I'm gonna want your help on this one. This one's just giving up the ghost. Everything is. I think the most important feature of your rational functions is the vertical and horizontal asymptotes. So let's start by finding those. Vertical asymptotes. And then horizontal asymptote. Try and find your vertical and horizontal asymptotes first. If you're watching this at home, you can fast forward till it's unpaused. But see if you can't find your vertical and horizontal asymptotes first. Then work with the domain. Try and find your x-intercepts and your y-intercepts. That should be a good start.
You need 6x minus 18 in the numerator. When you put in the denominator, you need parentheses for the denominator, and then parentheses around x minus 6. And then another parentheses, x plus 1, and the double parentheses at the end. If you just did a single parentheses, you divide this by this, and then times by x plus 1, which would really mess up the graph.
You can help each other out. Here by myself, I don't have Kata to walk around and help out. But start by finding the vertical asymptotes. What do you have to do to find the vertical asymptotes?
This is, so P is greater. It's the degree of P, the degree of the function. So this is, correct.
What if the denominator is 0? I mean.
What would we use?
Well, if it's not one of these other cases, then you wouldn't have
It would sit there
any kind of horizontal guessing.
Oh, okay.
Mhm.
I think that
So it's larger than more.
Yep, that's what I mean.
Yeah, that's not gonna have. That's not good.
This way.
Those are your vertical asymptotes, and yeah, your horizontal asymptote right as well.
Okay.
Sure where to start.
Yeah, that's right. See if you find the x-intercept and the y-intercept.
If you find the vertical and horizontal asymptotes, find the x and y intercepts.
less than the degree of the denominator? Or is the degree of the numerator 1 bigger than the degree of the denominator? So this is like a 6 and this is a 5.
So for our vertical asymptotes, we want to find where the denominator equals 0. So set the denominator equal to 0. So our function was s of x equals 6x minus 18 over x minus 6 times x plus 1. So I've got x minus 6 times x plus 1 equals 0. And I hope that you can read this stuff off. Hope you've been solving enough of these that you can just look at it and tell me, where am I going to have vertical asymptotes? Thank you all. 6 and -1. Now, since we're here, let's take care of another little problem that's kind of part of this, and that is, let's find the domain. So for our domain, we can't have x equal -1, and we can't have x equals 6. So it's everything in between here. So it's -infinity to -1, union, -1 to 6, union, 6 to infinity. Yay. Nice. Nice. How about the horizontal asymptote? Well, first thing first. Are we okay with our domain and our vertical asymptotes? Those are a couple easy points, even if you forget some of the other stuff. So our horizontal asymptotes, we got to decide which of these three cases we're dealing with. So you've got the degree of the numerator is bigger than the degree of the denominator. The degrees are equal, or the degree of the numerator is 1 bigger than the degree of the denominator. Now Mina had a good question. He goes, well, what if it's none of these? If it's none of these, it doesn't have a horizontal asymptote. So that's okay. Let's take a look at our function. S of x is 6x minus 18 over x minus 6 times x plus 1. What's the degree of the numerator?
1.
Right, so the degree of the numerator equals 1. What's the degree of the denominator?
2.
X times x is going to be an x squared. So the degree here is going to equal a 2. And since the degree of the numerator is less than the degree of the denominator, then which case is that?
Y equals 0.
Yeah, case A, y equals 0. That's going to be your horizontal asymptote. Nice. All right, so we got a couple vertical asymptotes and a horizontal asymptote. We can also find where the graph crosses, say, the y-axis and the x-axis. So our y-intercept, for that, we're just going to set x equal to 0. And I don't think we're going to get exactly 0 here when we do that. You're going to get 6 times 0, so s of 0 minus 18 over minus 6 and plus 1. So let's plug in a 0 for x. Now, if you've already got this programmed into your calculator, that's fine. When you do all the arithmetic, you get -18 divided by -6, which is 3. So the graph should cross at 0, 3. So 0, 3 is your y-intercept. Now the x-intercepts. Let me say something about the x-intercepts in general. When you're trying to find the x-intercepts, they're going to be exactly where the numerator equals 0. So x-intercepts set the numerator equal to 0. If you set the denominator equals 0, you'll find the vertical asymptotes. If you set the numerator equals 0, you find the x-intercepts. So I get 0 equals 6x minus 18. And if I solve for x, I end up with x equal 3, which I flipped it around there a little bit. That's okay. So I got the points 0, 3 and 3, 0. Do all these things line up on our graph? Do they match what we expect? Well, let's find out. Let's see if this matches what we imagine based on all the information we've picked up from this. So I'll shut this one off. I'll turn this one on. And let me zoom in a little bit. On Desmos, if you hit the home button, it'll take you back to kind of a standard window, just like we can on our TI-84s. So here's our graph. Okay. Want to put in the asymptotes? Sure. Let's put in the asymptotes. And again, I kind of wish I would have put them in with dash lines. There we go. So there's your dash lines. We got one at 6 and one at -1. Looking pretty good. I'm not going to draw the line y equals 0 because that's where these graphs eventually are going to go. And you're not going to really see it because it's going to be the x-axis already. All right, there's one last question we got to answer on this, maybe two last questions. So let's go back to the actual handout for that part of it. Now, on a test, if I ask you for the x or y intercepts, I'm just looking for the numbers, you know, whatever x equals or whatever y equals. Here they actually want, for instance, 3, 0 or 0, 3. Vertical asymptotes, that was when x equals 6 and x equal -1. Horizontal asymptote was y equals 0. But how about your domain and range? Well, we've already done the domain. That was -infinity, -1, 1 to 6, and 6 to infinity. How am I going to figure out the range, though? What do I have to do for that? What is the range? What does the range correspond to?
1.
Yeah, the range is the y values for this graph. Now, if I didn't have this middle piece, my range would not include 0. But because I've got this middle piece, this graph will go all the way up to positive infinity and all the way down to negative infinity. In other words, your range is all real numbers. So negative infinity to infinity. How do you get that extra point for an answer like this on the exam?
Capital R.
Yeah, that script R, capital R. That's basically math speak for all real numbers. Let's remind ourselves, all right, before I go on, are we okay with what we've done with example E? These are just a lot of good little things here that you should be able to pick up when you're looking at these graphs. Keep in mind, I'm not going to take away your graphing calculators from you on this. Although in graphing this one on the graphing calculator, you have to be a little bit careful. So to put this one in takes a little finesse. Hannah, you had a question?
Yeah, for this example, when we found the x-intercepts, why did we set the numerator to 0? Isn't it usually y? Are they the same? Or?
Well, so it's a good question. So let's say you've got some polynomial, and I'm just going to do this in general terms here to try and answer your question in general. So we've got r of x equals p of x over q of x. And I want to know, as you said, the x-intercepts. So that means effectively setting our y equal to 0. That is our y.
Okay.
So you get 0 equals p of x divided by q of x. Now you have to solve this. Well, then you're looking at that going, man, this just looks a lot tougher than I want to deal with. And then you get this great idea. Like, well, let's multiply both sides by q of x.
Oh, okay.
And what happens when I do that? On the left-hand side, I get 0. And on the right-hand side, those cancel. So basically, this equals 0 where the numerator equals 0. So that's why
Oh, okay.
That's why we can ignore where the denominator equals 0 when we're trying to find the x-intercepts, is because it's not going to really matter where the denominator was 0. We're just looking at where their numerator is 0.
Okay.
So good question. Thank you. Anything else on this before we move on? Okay. Let's remind ourselves a little bit of this notation. So this is the end behavior notation that you'll see from time to time. And, you know, it's just basically a shade of things come. Kyle, question?
Were you gonna show us how to?
Oh, yeah.
Thank you.
Yeah. Going back here, yeah, before I get onto the annotation, let's discuss how to put this into your calculator. Because unless you're careful, you're going to put it in the wrong way. You've got to put parentheses around the numerator, 6x, 6x minus 18, parenthesis, divided by, and now in the denominator, you need 2 sets of parentheses. One for the entire denominator, and the other for your x minus 6. And then another set of left and right parentheses for your x plus 1. And then 2 parentheses, one to close off that binomial, the other one to close off the denominator. If you only put one set of parentheses, then it would divide 6x minus 18 by x minus 6, and then it would cancel, or then it would multiply by x plus 1. So it would give you a much different graph than what you're expecting. Now, what's the workaround for that? That looks kind of ugly. The workaround for that, if you've got a more modern calculator, is hit the alpha key, then the y equals key, and choose the first option. So alpha, y equals. Now you can enter it without all those extra parentheses, 6x minus 18, and then x minus 6, which you still need parentheses around, but you don't need a double set of parentheses in the denominator anymore. And these should both give me the same graph. Let me take kind of a quick look at my window here. Yeah, negative 10 to 10, good enough. There it is. And briefly it was blue before it got colored over by the red graph, but they're the same graph. So, thanks, Kyle.
Yep.
Okay, let's look at the end behavior. So we're referring back to this graph. The end behavior of a function is what happens when you're getting out very, very far out the x-axis. So, for instance, as x approaches infinity, let's look at what happens to this graph as x approaches infinity. So x approaches infinity, that's what happens when you go out the graph this way. And where does the y coordinate look like it's heading to as x approaches infinity? Where does it look like it's leveling off at? 0. Thank you. 0. So that would be your answer. As x approaches infinity, y approaches 0. Let's try that in the other direction. As x approaches negative infinity, so this means we're going out the x-axis that way. Where does the y coordinate go?
Zero.
It's the y coordinate as you're getting farther out the x-axis. That y coordinate is getting closer and closer to
Negative infinity.
the y coordinate. The y coordinate is getting closer and closer to 0.
And then he said 0, he never. We both said 0 and you just.
I heard a different. I heard a different.
Yeah. Because no. We said 0.
Zero is right. Zero's right. I didn't say it was wrong. I
I
heard.
was saying negative infinity.
Yeah. Yeah. That's the one that's the one that I corrected. Was the negative infinity.
You had.
As x approaches negative infinity, y approaches 0. So there are other types of, these are called limits that you could look at. But I mean, we're just worried about the end behavior, which is what happens with x and approaches positive or negative infinity. What's happening to the y's? We saw a lot of that when we looked at the end behavior of our polynomials back in section, was it 3.3 maybe? Let's see, 3.3. No, 3.2. So you're seeing that like here. As x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches positive infinity, etc. That's your end behavior stuff that I would suggest you know, I don't know, sometime maybe by Wednesday. Okay. Let's see. Let's keep going. Let's flip over to the backside and look at this one. Example H. So something a little bit different about this one. Let's find its vertical asymptote first, and we'll work on horizontal asymptote second. So this is example H. I've got r of x equal x squared plus 3x over x minus 7. So I want you to do two things. I want you to find the vertical asymptote and decide which case this is going to be for your horizontal asymptote. So I'll remind you of your cases right here. Give that a second. See if you can't figure out which case you're dealing with here and what the vertical asymptote is. Actually, no.
Yeah.
That and decide which case you want for the horizontal. Ah, very good. Oh, we're doing example H, not example G. Oh. Only if you want to write. So we always, you have to count all the coefficients even if they're zero. So you're doing good. Which case? Just tell them which case. Yeah, okay. Which case does it seem like this applies to? Just tell me the case.
So as far as the asymptote, I mean, not the vertical asymptote, the other one, tell me which case applies here. which case do you think applies? Is it A, B, or C?
Seems like none of them.
None of them?
Yeah,
Okay.
because P is supposed to be less than Q in here. Isn't P greater?
All right.
Is degree 2 up top and degree 1 at the bottom?
Let's take a look at these. So let's start with the easy part. Let's get the easy part. In any test, get the easy points first, right? So quick easy point here. Hermine, how am I going to find the vertical asymptote?
X minus 7 equals 0.
Yep. X minus 7 equals 0.
All right, and that's going to happen when x equals 7. Great. Let's take a look at these things and notice that the degree of the numerator is 2. What's the degree of the denominator? So looking back then, which of my 3 cases does this apply or applies here? Is the degree of the numerator less than the degree of the denominator? So it's not case A. Are those degrees equal? Is the degree of the numerator 1 more than the degree of the denominator?
Yeah.
So it's case C, right? So it's case C. Now, in that case, what did I suggest you do? Well, I suggested you find the quotient. So you're going to divide the numerator by the denominator, and that quotient is going to be the equation of what's called your slant asymptote or oblique asymptote. Now I'll just throw in here the word slant. I think that WebAssign or the book uses that. I like oblique asymptote, but whatever. Now, let's see. As far as this is concerned, we've got to divide the numerator by the denominator. So divide x squared plus 3x by x minus 7. Here's a good chance to practice our synthetic division. So if I'm going to do this synthetically, what can I write here? Well, let's start out with a 1 and a 3.
Oh, so
Mina, is there something else I have to write here?
A 0.
It's not written here, but it's understood that there's a 0 for the constant term. So we got to write that constant term here. Good. Now, personally, when I do these things, I put that vertical bar here. Brandon, that vertical bar is a reminder as what? What's it tell me here?
The remainder.
Yeah, that's a remainder. Good. And Dalen, what number goes out in front for my synthetic division?
-7.
The -7 or +7? Amber?
Positive 7.
+7. So a +7 here. Ryan G, I have a personal preference of putting a 0 here. Where does this go after that? What do I have to do?
And just put a 1 below it.
Put a 1 there. Keep going.
7,
7.
10,
Mm-hmm.
70,
Nice.
and 70 again.
Perfect. Add going down, multiply to go up, etc. Great. Kyle, what does this tell me about my quotient remainder? What should I write? X squared plus 3x plus 0 divided by x minus 7 equals what? What is this telling me here?
X plus 10. Well, I got like X plus 10 and then with the remainder of, I got negative 70 and then with that over.
All right, so it's going to be x plus 10
Yeah.
plus 70 over x minus 7. And this is the part that I need right there. So that's going to be y equals x plus 10 is the oblique asymptote. But that's going to happen when your degree of the numerator is 1 bigger than the degree of the denominator.
What does that say? Oblique asymptote?
Oblique asymptote. Or you could also put the word slant asymptote. That'd be a synonym in this case for oblique. The rest of this stuff, you can play around with. We can find where the numerator equals 0 at x equals 0 and x equal -3. Those are going to be the roots of this polynomial. We know it's oblique asymptote. So if you were to graph this, I would start by graphing, for instance, the oblique asymptote, which I've done for you here. I'll keep that in yellow in keeping with what I've got on the other sheet here. So the equation of this is y equals x plus 10. Then I've got a vertical asymptote right here at x equals 7, I think it was. Make sure that when you label your asymptotes, you do x equals something or y equals something. If I did take a peek at where this was equal to 0, the numerator equals 0, I get 0 equals x squared plus 3x. Are you going to pull out the quadratic formula for this one? I really hope not.
Yeah.
Yeah, you could. Pulling out the quadratic formula here is like squirrel hunting with a bazooka.
Extra points for it.
No, actually, I'd have to restrain myself for not taking off more points because you're working so much harder than you have to.
It always works. It's gonna work every time.
It always works. It always works.
Always works.
It always works.
Yeah.
So you're going to get two places where this graph equals 0, at x equals 0 and at x equals -3. So that's going to be here, and yeah, it's going to be really close to that.
Grab the x equals 10 and take that at x equals 7.
X equal -3 is going to be about there. So it's just going to peak above the x-axis for just a moment, right there, and then go down. Overall, your graph is going to look something kind of like this. Peak above and then go down, and then you're going to have behavior like this.
So that's a separate line, or?
Well, these are just asymptotes. They're not really your graph. The only part of your graph is really going to be in green.
So asymptote can curve like that?
Well, in this case, you've got a slanted asymptote. That's going to happen when the degree of the numerator is 1 bigger than the degree of the denominator. So that's what's happening on that one.
Yeah, it's good over.
Yep.
Not to the,
No,
to the,
I mean like scooch the paper.
yeah.
Which way?
Right.
This one?
No, that's
This one.
Escuche.
the graph right there.
Escuche.
Escúchame. Excuse me. In Espanol. All right. Any follow-up on this one? We okay with?
Why you put it on the x equals 10 though? What are you talking about? On the orange graph, that's 10.
Oh, I'm sorry. Yeah, it should be over a little bit. All right, fine. Here.
Mm-hmm.
No, you're not.
With that, 'cause I'm just like, I thought it was 7, but that's what it says.
There we go.
Oh my God.
Get up off his back.
Y equals x plus 10.
Boy, girl.
X equals 7. Still have my points here and here.
Professor Parent, remind her that you got a breaker test. Tell her to get up off your
So when I when I grade test, fortunately for her, I don't look at names.
You got to put them in, right?
I do, but that's after I total up the points.
Yeah,
So
Oh my gosh.
I look at everyone's first page. All right, I don't look at the names. I grade everyone's first page without looking at names. I flip it over, I grade everyone's second page, and so on. So I don't really look at names until I've totaled up the points. So
By then, it's
I don't. I try and be as objective as I can. There's one more thing we got to cover, take care of in this section. It's not something I'm really going to test you on, but it is something that you could see in terms of
Extra credit.
no. I don't know. I think between now and Wednesday, you've got enough to keep your hands full. But it might appear in the homework. And it's going to go all the way back to example B. I know, I'm sorry. Don't shoot the messenger. So let's look at example B. Don't egg them on, Johan.
I'm sorry.
I know, it's fun. Example B. R of x is x squared plus x over x plus 1 and 4, bless you,
Type.
4x,
Bless.
bless you.
that's a third one.
Yeah. You've exhausted your supply in the next week.
You sound like an engine starting. Sorry.
All right, let's finish this because we really need a break. Now, at first glance, where does it look like there's going to be vertical asymptotes for this problem? X equal -1 and x equal 3. Perfect, thank you. But then when you plug this graph into Desmos or your graphing calculator, you'll see something weird. Let's go up to example B, and, well, I can see my asymptotes for x equal 3, but instead of a asymptote at -3, or excuse me, at -1, I've got this hole in the graph. There's a hole in the graph, and if you trace very carefully on your graphing calculator, you see briefly this little point where, there you go, I nailed it perfectly. -1, it says undefined. It's like, well, wait a minute. I expected a vertical asymptote there. What's going wrong? You can see what's going wrong if you look at, let's see, if you look at this and factor the numerator. So how do I factor the numerator?
X, just take out an X.
Yeah, take out an x. And it gives me x times x plus 1. What does it look like it's so tempting to do?
Oh, cancel.
Cancel those. Now, before you cancel these, x equal -1 is still not part of the domain. You can't use that because you'd be dividing 0 into something. In this case, you'd be dividing 0 by 0, but that's still undefined. So that's kind of strange. Now, other than that, if you realize, okay, let's just not let x equal -1, then you've got x over 4x minus 12. That's what this graph's going to look like other than at x equal -1. So at x equal -1, the graph's just not defined. And that's why you're seeing that hole in your graph right here at -1. And I've kind of made it a little bit more dramatic here. So -1, yeah, there is a hole. And if you cursor over it just right, you'll see that. Now, it's hard to get that to show up on your graphing calculator. It takes a little finesse. I'm not going to ask you to worry about it. But in the off case where you have a term that cancels from numerator to denominator, then the graph has a hole. So the graph of r of x has a hole
At -1.
at x equal -1.
Can you explain that other part again? About how you can't cancel them?
Well, you can cancel them, but you just got to remember that the original function is not defined when x equals -1. So if you want to cancel them, you just got to put this little reminder, okay, I can't put in x equal -1 here because the function's not defined at that point. We'll actually play around with that more in calculus, to figure out what to do to fill in that hole if you run into something like that. But for now, just realize that the graph has a hole when you have a common factor in the numerator that can cancel with something in the
So
denominator.
whenever you can cancel them, that means there's a hole.
If you have a term in the denominator that cancels with the term in the numerator, then at that point the graph's going to have a hole. So, and I could create graphs with holes wherever I want just by having terms that cancel at that value of x. Okay, anything else?
One last question. When it does cancel, that means that the hole is at
The hole is at where
Whatever's canceled.
this term was equal to 0.
Okay.
That's where your hole is going to be in the x direction. You'd have to figure it out in the y direction, but that goes above our pay grade. That's definitely in the realm of calculus that we'll figure that out. All right. Good luck with this stuff and thank you.